Alright, hello class. In this video we are going to move on to chapter 3, which is all about the basic topology of R. And whenever you hear the term topology in mathematics, it's usually talking about sets and properties of sets. And that's really what we're going to talk about in this chapter. And specifically, we need better definitions for open set and closed set. All right, so that's the motivation here, is we need better definitions of closed and open in order to be useful for, actual formal proofs. Okay. Now, some analysis books and classes will actually start with the topology, and you might understand why that might be, because this is all about the nature of sets, and our axiom of completeness was all about the supremum of sets, right? So it might make some sense to do that. However, this book and in this particular class, we are tackling this after we have the idea of limits, because it ends up being easier to do this, in my opinion, after you have sequences and limits. Okay, so in my opinion, this is slightly easier to do now. Okay, ever so slightly easier. It of course won't be easy at all. But how this chapter starts off is an interesting discussion on the Cantor set. And that's what 3.1 is all about. It's a discussion on the Cantor set. And you may recognize that name, Cantor. He was a mathematician we were talking about a lot when we were talking about cardinality. And we were talking about proving that the reals are uncountable. There's Cantor's diagonalization method and Cantor's theorem and all these things that he brought to the table when it comes to classifying infinities. He also brought us this really neat example of a set, and that kind of, it's a really nice thought experiment. Okay, it's a it kind of stretches our imagination when it comes to what we think of as subsets of the real line. Okay, so let's get to it. What is the Cantor set? Okay, well, here's how we do it. We start by calling the set C naught the closed interval from 0 to 1. Okay, then C1 is the set, or the interval, where we take C naught and remove its middle third. So it's C naught with its middle third removed. So specifically, C1 is going to be C naught, which is actually 0 to 1, and we're going to remove the set 1/3 to 2/3, and we're removing the open middle third. I guess I should say that it's the open middle third. Okay, so what ends up being left is 0 to 1/3 closed, union 2/3 to 1 closed. All right, so if we were to look at this on a number line, let's say this is 0, this is 1, and I'm going to split it into thirds. So here's 1/3, and here's 2/3. Okay, and what we're going to do is remove, the middle third. And keep the endpoints. So we're removing the open inner third. So we're left with the endpoints 1/3 and 2/3. Okay, then C2 is C1 with the middle thirds removed again. So it's the first piece, 1 to 1/3, minus its middle third. And then, so that would be, what I'm going to do, I'll do this one in red. Okay, so here I just duplicated C1 and moved it down here. All right, and in red here, I'm going to chop this piece into thirds. And this would be, if we're chopping an interval of 1/3 and a third, these would be ninths, right? This would be 1/9, this would be 2/9, and this would be 3/9, which would be 1/3. So we're actually removing this middle third here. So let me write that up here. We're removing the open set 1/9 to 2/9. Okay. And then we're also removing the middle third of this second piece. All right, so we'll cut this into thirds. All right, so 2/3, that's 6/9. So this should be 7/9, 8/9, and this, of course, would be 9/9. So we are removing the open set 7/9 to 8/9. Okay, and for me, it's easier to just see what's happening when you look at the graph. Okay. And so here's C2. All right, we're removing the middle thirds of everything we have left. Pretend I've drawn this all to scale and that it looks, decent. And then, well, C3, whoops. I don't know what's going on there. For C3, we do it again. We remove the middle thirds again. Okay, so here's C3, and I'll do this next piece in orange. We're going to chop this into 3 pieces, this into 3 pieces, this into 3 pieces, this into 3 pieces, and then erase or remove the middle third. And we continue doing this on and on and on and on and on. Okay. For each particular C. So for C4, then we would remove the middle third out of these guys, and we'd remove the middle third out of the next. Okay, so each next little piece of this gets smaller and smaller and smaller, because what we do is we continue, so that would be C4, and then C5 would be, I'm getting now to just basically dots. But each little yellow line here would give me actually 2. They're not actually dots, they're just very small lengths. However, right? If we were to zoom in on one of these, right, this would have 0 to something, like, right, since this is C5 and this is the leftmost interval, it would go from 0 to 1 over 3 to the 5th. Okay, which is a very small number, but we can continue the process, right? We can just remove the middle third, and that would make a piece of C6, right? So the green was C5. Then we can do it again. Okay. And so maybe what I should do here is show that if this is C5, C6 would look like this, or at least just part of C6, which would be like right here, would look like this. The next piece would look like this. Okay, and as far as we zoom down, we're going to get smaller and smaller versions of basically the same idea. We just have a smaller starting set. Okay, and all these little guys that I've just drawn are just off of this leftmost piece of C5. Okay, so this is what the left piece of C6 would look like. C7, C8, C9 would be even smaller. Let's use red here. Okay, and then C10 would be even smaller, and we could zoom into this piece and start the process all over again. And that would just be the rightmost piece would be the 0 to 1 over 3 to the 10th, and continue the process over and over and over again. Now, that comes all the way from a starting set. Well, our C0 was just 0 to 1, but the Cantor set, so this is just the sequence of sets, okay? So the Cantor set is, okay, so the Cantor set itself, okay, is the infinite intersection of all of these CKs. So we're going to take K going from 1 to infinity of all these CKs and take the intersection. So that means we're only going to take the pieces that are in every one of these, so only the overlap. Okay, so us only taking the overlap means, well, we won't take any of this in here, but we'll take this stuff, but then we won't take any of that middle stuff or that middle stuff. And what ends up happening is, if you think about the points that are going to be in every one of these, what we would do is continue to zoom down and down and down and down, and you would have, if you kept going, the rightmost piece for every one of these, okay, is 0 to 1 over 3 to the n. Okay, and that's just the rightmost piece, which shrinks down to 0. However, it's a closed set, so it's always going to contain these. And one other thing to mention, that if you start instead doing this process here at 1/3, notice in all of these, 1/3 is always in them. So RCN, whoops, went off the screen there, RCN, if we continued on, it would also have a piece that would have 1/3, and then this would be, say, 1/3 minus 1/3 to the n. Okay, something very small. All right, so it turns out that the Cantor set has all of the endpoints that we've started with and all the endpoints that we will create. So 1/9 will be in every one of these. 2/3 will be in all of them. 7/9, 8/9. Okay, all of those points are going to be, all those endpoints are going to be in this intersection. All right, so to write some of this stuff down officially, every endpoint will be in each subsequent CK. All right, so 0 is in Cn for all n in the naturals. 1 is in Cn for all n in the naturals. 1/3 will be in every Cn for all n in the naturals. Okay, 1/9 will be in every Cn for all n greater than or equal to 2. All right, so this implies that basically that 0 will be in C, 1 will be in C, and basically every 1/3 to the n will be in C. Okay, and this is since 1/3 to the n is in C sub n, and 1/3 to the n is in every CK for k greater than or equal to n. So it's in every subsequent CK or Cn. So that's what I was basically saying here. Basically, every endpoint we create is going to be in every subsequent set we've created in this. Okay, so the question then is, well, first, but from this, since 1/3 to the n is in C, okay, and this will be true for all n, okay, this implies that C is at least countable. Okay. Here's the crazy thing, though. So crazily, C is actually uncountable. Okay, so this is kind of strange because we would expect that at the end C is probably just a bunch of little tiny microscopic sets that we can't really see, and actually there should be none in the middle here. right in the middles of the middles. So really, it should just be like lots of tiny, 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 tiny sets, right, that we could never see, because we could always zoom in and get smaller and smaller and make them smaller and smaller, and you know, it's just this smattering of lots of little tiny sets, and we can't have any in this middle piece either. Okay, and this is often called this idea of having tons of little tiny minuscule sets. This is often called Cantor Dust, which I think is it's a very cozy name for this. Okay, so how can we show that C is countable, or sorry, uncountable? It's pretty, hopefully fairly clear that it's countable. To show that it's uncountable is actually kind of clever. Okay, so we're going to let X be in C. We could go to the process to prove that C is non-empty, but we have a nice grasp of that, hopefully, so far, that you know, 0 is definitely in C. Okay, so let's let X be in C, just some arbitrary X in C. Okay, then we can associate or equivocate. I like that word. We can equivocate. Of course, I have no idea how to spell it. It's probably equivocate. We can equivocate a sequence A sub n to X in the following way. Okay, so AN is going to be a sequence of basically just zeros and ones. Okay, actually, instead of calling it AN, oh no, I could call it AN. That's fine. It's a sequence. Okay, but it's going to be a sequence of, you know, A1, A2, A3, A4, A5, A6, etc., where each A sub n is either 0 or 1. Now, here's how we assign it. Okay, so let's go back to our 0 to 1. Okay, and let's say our X value lives, let's say it lives here, right? Okay, now I want to assign its sequence AN. So here's how we do it. Okay, when I jump to C1, right, we remove the middle third. And when we do that, X is either going to be on the left side or the right side of C1. Okay, so X, let me write here, X will either be on the left or right side of C1. All right, it's going to be one or the other. Now we know it's in C1 because we started by saying it was in C. If it's in C, then it has to be in C1, since C is the countable intersection of all of these. Okay, so if X is on the right side, so if it's on the right, we'll let the first term be 1. So if x is on the right, in fact, in other words, closer to 1, we'll set a1 to 1. If it's on the left, set a1 to 0, since what we're saying is it's closer to 0. So in this particular example I just looked at, x is on the left side, so a1 will be 0. Okay, now we're going to ignore this piece and then just look at the remaining piece. And so we'll remove the middle third. Okay, and now we're looking at C2. Now in C2, we're only looking at the piece of C1 that it was in. We're discarding this. Okay, so we can actually, I'll just X this out. We don't care about this anymore because we know that X is not there. Now, we're going to do the same thing. Is X on the left or the right side? Well, it's on the left side. So, since it's on the left side again, we'll put in another 0. Okay, now we'll ignore the piece that's not in and move to C3. All right, now C3, I may not have done this very well, but this makes me think X is probably an endpoint. Okay, and so I'll put a 1. Okay, and then I'll X out the piece it's not in again. And now, since, let's say this X is the endpoint, and it looks like an endpoint, it's going to continue to be, as we continue to remove middle thirds, it's going to continue to be on the left, so every other term in this sequence will be zeros. Okay? And this is essentially our X. Let me show another one just to kind of give you a sense of how this is working. Okay, so let's say, this is our 0 to 1. Okay, and I'm going to make, this time I'll start searching for Y. So let's say Y is about right here. Okay, so when we remove our middle third, okay, so Y, I'm going to say it corresponds, let's call this sequence Bn. In the first step, it's on the right side, so I'm going to put a 1, and then I'm just going to ignore what's left here. Now I'm going to remove the middle third again. So here, I'll remove the middle third. And once again, for C2, it's on the right side of what's left. All right, so we'll ignore this now. And we'll remove the middle third again. And now it's on the left side. Right? The side closer to 0, even though it's not over here near 0 from what's left, what we're actually looking at. Okay? So I'm going to put now a 0. Because now I was basically saying, okay, you jump this way, then this way. Now we jump this way. We're in the left side. So now I'm going to ignore this piece. And actually, it looks too close to call as far as like which side it's going to be on. So I'm going to zoom in. Okay, so I've zoomed in. and let's say our y, it's going to be kind of close, looks close to the middle, but I'm going to pretend like it's actually over here. Okay. Then when I remove the middle third, okay, I'm trying to not make it an endpoint. Okay, now it's 0 again because we're going to jump to the left side. So it's almost like a sequence of left, right, left, right, left, right, but we're just doing 0, 1, 0, 1, 0, 1. Okay, now I will move the middle third again and ignore this piece. And when we do it again, this y is now on the right side. So we'll put a 1 because now we're jumping to the right side, and then we would zoom in on this piece. And we would continue this process over and over and over again. Okay, so what we're essentially doing is each element, so every element in C can be uniquely defined as a sequence of zeros and ones that act as almost like a map to get to the point. So they act as a map or a set of directions to find the point in C. Right? So here it's 1, 1, 0, 0, 1. Okay, so this tells me that Y, I'm going to go right, right, left, left, right, and then just continue to follow the directions. Okay? Now, since I can do this uniquely, this means that, and I'm not going to go into huge details here, okay? I don't think neither the time nor I don't think it would be that helpful to do. We can actually, with this process, this gives us a bijection between C and the set of all sequences containing zeros and ones. Okay. Okay, so as described in exercise 164. So in exercise 164, we were given the set S, which was all the sequences with A1, A2, A3, where each AN is either 0 or 1. Okay? So, what we have here is that essentially C is cardinal to S, and by exercise 1.6.4, S is uncountable. All right, now this was actually one of the homeworks that wasn't able to be truly assigned and turned in because of us moving to distance learning. But we can prove this using Cantor's diagonalization method. All right, so since we didn't get to go through it with, say, a homework, let me show briefly how you would prove that S is uncountable. You would suppose, to the contrary, that S is countable. Okay, so there is a way to index every sequence in S. Okay, so we could say, all right, sequence 1 is, let's say, A11, A12, A13, A14, A15. I'll just take it out to 5. Then S2 would be, let's say, A21, A22, A23, and I'll continue this out. You don't need to watch me write every one of these. Okay, so we have a list of our sequences like this, and we can itemize them or index them since we're assuming it's countable. So all of S can be written as the set of S1, S2, S3, S4, S5, etc. Okay? All right, now we're going to approach this like we did using Cantor's diagonalization method. So we'll utilize Cantor's diagonalization method. Always a tough one to spell. Where, and I forgot to mention all of these. A sub ij are either 0 or 1. Okay, that's how we've created all of our sequences. So we're going to utilize Cantor's diagonalization method in that we create a sequence. Let's call it x sub n, okay, where each x sub n is defined in the following way, right? X sub n is going to be equal to, well, it would be 0 if a sub n is 1, and it will be 1 if a sub n is 0. In other words, we just take the diagonal and we create a new sequence by taking each one of these and swapping them, either from 0 to 1 or from 1 to 0. And because of this, defining xn in this way, so it really should be this sort of, oh no, I did it right. All right, so defining, let's say x, which is equal to the sequence xn in this way, we have that x is not equal to s sub k for any k in the naturals. Therefore, x is not in S. However, S is the set of all possible sequences right? It's the set of all possible sequences made up of zeros and ones. So X is in S. All right, and there's our contradiction, that if we assume that this set S is countable, we can create an X that does not live inside of it, proving that it's uncountable. Okay, now this is not a super formal proof in any way, it's more like a sketch of a proof. So what this essentially gives us, therefore, C is cardinal to S, implying that the Cantor set is uncountable. Which is a fairly strange result. It's an uncountable set that we would have trouble seeing. I mean, we know that something like all of, say, 0 to 1 is uncountable, right? That makes sense. That's all the real numbers and all the, all the rationals and irrationals and everything like that. But what we're doing with the Cantor set is essentially breaking it into multiple pieces over and over and over again, okay, until it looks like there's nothing left. Yet, it's actually uncountable. So hopefully, I hope that this discussion has actually helped broaden your thoughts of how sets can be defined on the real line, and hopefully shows a good motivation into why we need a more rigorous approach to talking about sets. Because the question is C open? Closed? Okay. How we've talked about open and closed so far is just in terms of intervals, right? We have like the interval a to b, that's closed, and this interval a to b, that's open. But what about C? Is it open or closed? All right, so this is the motivating factor here, of that, oh, well, it seems we need better definitions, or just better ways to talk about sets. Thanks to how weird they can get. Okay? All right, so in the next video, that's what we will start to do. We will start plugging away at this, and I will catch you all on that one. Cheers.